In this video, we're going to look at how to find the range of a function. Some of these will be polynomials, rational functions, exponential, log functions. It's a little bit easier to find the domain than it is to find the range. So I'm going to focus on the range, but just to point out the difference in the two, how they're similar. So this is the function f of x equal 3x plus 7. You can also call it y. So let me just go say this is y equal 3x plus 7. And of course, you should recognize this as a linear function. In other words, the graph is a straight line. Now, if you have the function sought for y and you wanted to find the domain, all you have to do is find out what restrictions you have. So in other words, here we have 3 times x, where x is a real number. With domains and ranges, we deal only with real numbers. So if I put any number in for x and multiply it by 3 and add 7, will that give me a real number? If you can answer yes to that, then the domain is all real numbers. And you could write it in interval notation and say domain would be negative infinity to infinity. I go the other way. If we want to find the range, solve the equation for x. Bring the 7 over, y minus 7 is equal to 3x. Divide by 3. So now you have x is equal to y minus 7 over 3. So now instead of x, in terms of x here, I have this x in terms of y. So I look over here on this side then. Is there any restriction on this? If I take any number, subtract 7 from that, and then divide it by 3, will that give me a real number? If you can answer yes to that, any number will work. So the range would also be negative infinity to infinity. Let's look at one like this. Let's say f of x, or I'm going to call it y, over 1 over x. I have y solved in terms of x. So we look on this side. Is there any restriction? 1 over x means 1 divided by some number x. Can I put any number there? Can I divide 1 by any number? Well, you can do it with any number except 0. X cannot be 0 because division by 0 is not defined. So in this case, I would write, I'll go ahead and write it in set builder notation, or set notation. And this means when I write it this way, it's the set of all x such that x does not equal to 0. I could also write it in interval notation, but this is a little bit easier. In other words, in a numbered line, you'd have 0 right here, and this would be anything greater than 0, like this. Or you could go negative infinity to 0, parentheses here, because the 0 is not included, together with everything greater than 0, 0 to plus infinity. Now, take the same function here. And solve it for x in terms of y. So multiply by both sides by x. I get this. X is canceled on this side, and then I solve for x. So divide by y. X is equal to 1 over y. What restriction do we have? Again, y cannot be 0, because division by 0 is not defined. So for the range, similar to the domain, would be the set of all x. Set of all y, such that y does not equal to 0. And I could write that in interval notation also. Now, it's not always easy to solve the equation for x in terms of y, but if you can do it, you can get the domain, or the range rather. Now, if you know what the graph looks like, that'll give you an idea of what the range and the domain is. So let's say we have a parabola. Has vertex at 0, 2. Right there, 0, 2 is a vertex, and it's the type that opens up. You can see I pick a value at 0, 1, 2, 3, 4, and so on, and there's a value somewhere up there for y. Negative 1, negative 2, or negative 1/2, whatever you want to pick, there's going to be some value up there for y. But the smallest that y would be 2, right there. So for this one, the domain is all real numbers, negative infinity to infinity. The range, in this case, instead of all y, such that y is greater than or equal to 2. So you can get the range if you know what the graph looks like. You can also get it if you can solve the equation for y. So now we're just going to focus on the range. I've done some problems on dealing with the domain. These, we're going to look at the range. Now the next one, the y. Again, I'm just using the y instead of the f of x. Again, easy to find the domain in this one. You can see x cannot be 0. So let's look at what the range is going to be like. So let's multiply by x squared. Multiply both sides by x squared. get this over here. This side will be 2. X squared and x squared cancel. And then let's divide by y. Both sides by y. And this y will cancel. And then over here get 2 over y. 2 over y. So solving this for x, I'd have to take the square root of both sides. Plus or minus the square root of this here. So this will be 2 over y. And ordinarily, if I didn't have that radical there, was just x equal to 2 over y, I could just say, okay, I have y in the denominator, y cannot be 0. And that would be the range. Y cannot be 0. But because I'm under a radical here, the y cannot be negative either, because then we're dealing with imaginary numbers. So in this one here, we simply say that the range is going to be the set of all y. Y cannot be 0, but at the same time, it has to be positive. So if I put greater than 0 here, that will take care of that. And we have it. Now if I were to graph this function, I would get something that looks like this. The y-axis would be vertical asymptote, and the x-axis would be horizontal. So the graph goes this way, approaches the x-axis but doesn't touch, comes this way, approaches the x-axis and doesn't touch, so the y stays above. The y value stay, or the graph stays above the x-axis, which of course means that the y is going to stay greater than 0. The next one, f of x is equal to x to the third minus 3x squared plus 4x. Now, polynomials in general, the domain is always going to be all real numbers. The only thing you have to be careful about getting a value of 0 in the denominator of a fraction, because division by 0 is not defined, or having a negative number under a radical. And knowing typically what these graphs look like. Now, polynomial usually goes something like this. You can have one that goes like that. You might have one that looks something like this. Domain will all be, all of these will be real numbers, all real numbers. But notice this one. This one here goes this way, and then it goes up forever, down. If you picture this in a graph, y's will be positive up there. As this comes down, it'll be negative. But notice for this one, something like this, the y value is going to depend on these low points. So even though the domain is all real numbers for this one, the range, it's not, because it has loops and it keeps it above. So here's what you need to know for the polynomials. If you have an odd degree polynomial right here, and the coefficient of that first term, in this case, this could be a lead term of x to the third, or x to the fifth, or x to the seventh, as long as it's odd degree, those go up at one end and down at the other. And then here in the middle you have loops. Now if the coefficient is negative, all it means is it goes up on this side and it'll hit down. It's just reverse. Go up that way and then comes down over here. The range will still be all real numbers. So if this is odd degree, the degree of the polynomial is odd, the range will be negative infinity to infinity. Negative parentheses here. Negative infinity to infinity. That's your range. Okay, the next one, you should recognize this is a exponential function. And your exponential functions typically with base greater than 1, the base is always positive and not equal to 1. So if the base is greater than 1, say 1.5 or 3/2, or 2 or 3 or 4, then typically when x is 0, you get 3 to the 0. So without this 5 here, if it was just 3 to the x, this one would pass through. Replace the x by 0, you get 1. And then as you increase the value of x, positive values, it increases, it goes up. And then it goes something like this. And this point right here, 0.01. That's without the 5. So you can see this graph has a horizontal asymptote, which is the x-axis. So the horizontal asymptote is y equal to 0. Now, if you add a 5 to that, domain's going to be all real numbers. We're looking at the range though. If you add 5 to this, everything goes up 5 units. And it's going to pass it to have a asymptote right here, horizontal one, y equal 5. And it'll pass to 0, 6, go up like that. So without the 5 there, the range would be the set of all y, such that y is greater than 0. In other words, it has to stay above the asymptote. But in this case, we moved it up 5 units, so instead of 0, the asymptote is y equal to 5. So y has to be greater greater than 5. Or in interval notation, we could write it parentheses 5, comma, infinity. Either way. Either this way or this way. You would write the range. Now let's look at the next one. F of x is equal to x squared minus 4x plus 7. That's a polynomial, so we know the domains are real numbers. For all polynomials, the domains are always going to be all real numbers. The range change. And this one you should recognize it as a parabola. So if I can find the vertex, we can determine what the range is going to be. So what I'll do here is complete the square on this. This is x squared minus 4x. I need to add something to this to make it a perfect square. So since the coefficient of the square term is 1, I can take half of negative 4. And that's negative 2. Square it, I get 4. And add it here. But if I add it, I also have to subtract it. Otherwise, it's not the same thing we started off with. See, minus 4 here gives me the same thing back. So now I can write this as y is equal. This factors into x minus 2. This right here factors into x minus 2 times x minus 2, which is x minus 2 squared. And then 7 minus 4 is a 3. So now I have this in what is called the parabola in the vertex format here. You can write the quadratic function in the form x minus h, quantity squared, plus some number, we'll call it k. The vertex will be given by hk. So in this case, the vertex is 2 and 3. If I were to sketch a graph of this, I go 2 units over, 3 units up. Right there, this would be the vertex. And because the coefficient of the square term is positive, this would open up. It goes like that. So you can see at the smallest y you're going to have is the second component here, 3. All the other values for y, no matter what x you pick, are going to be above or larger than 3. So for this one then, we can say that the range b, a set of all y, such that y is greater than or equal to 3. That's your range. Notice I put an equals here because y can take on the value of 3, but then everything else to the left or to the right will be larger than 3. Again, notice the domain is real easy on this one. We look at this is a y, and then okay, for x, remember we can't have a 0 with the denominator, so x minus 4 is going to be 0 when x is 4. So for the domain, it's all numbers except 4. X cannot be a 4. We want the range, so let's do it this way. You can do the graph if you want to. It takes a little bit longer to figure it out, but let's do it this way. Now, it's not always that easy to do it like this, but try it. Let's multiply through by the denominator. So multiplying both sides by x minus 4. So this one cancels, and then I multiply it over here. So on this side, I'm left with x plus 2. Okay, multiplying through by x minus 4. And this gives me multiplied through by yx minus 4y is equal to x plus 2. Okay, so remember with this technique we want to solve it for y. So let's bring the x over. So we got yx minus x, and the minus 4y goes over, so we change the sign. Goes to the right side. We got yx minus x is equal to 4y plus 2. And then we want to solve for x, so let's take an x out of this. And divide both sides by y minus 1. It'll cancel on this side. So I come up with this, x is equal to, taking this equation and solving for x in terms of y, we get x equal to 4y plus 2 over y minus 1. Then you just look at the right side and see if there's any restriction on the y. If there isn't, then you can say that the ranges are real numbers, from negative infinity to infinity. But notice here we have y minus 1 in the denominator, and when y is a 1, this is 0. You cannot divide by 0. So for this one then, we would say the range is equal to the set of all y, such that y does not equal to 1. Okay, now the last one is a log function. Let's say this is the coordinate system. And typically, if you have, say, just y equal the log of just plain x to some base, I'll just say a. Let's say the base is greater than 1, because this is 2. And typically what's going to happen when x is 1, the log of 1 to any base is 0. So the graph is going to pass through 1, 0. And it's going to have the y-axis as a vertical asymptote. This graph is going to go something like that. So the y will have negative values over here. This continues forever down here. It goes up like that. Positive values over here. So positive to negative values. So there it looks like the range is going to be all real numbers. Notice the domain, x cannot be negative here. The log of a negative is not defined. So that's why this thing stays to the right of the y-axis. So if I asked you for the domain of anyone like this one here, the range would be negative infinity to infinity. Domain, x would have to be greater than 0. X cannot be negative, it can't equal to 0, it has to be greater than 0. But here we have an x minus 2. Is that going to change anything? Now all that's going to happen, this x minus 2, it's going to shift the graph. Instead of having an asymptote at the y-axis, it's going to be over here at x equal to 2. And this is 1, 2, and 3. And if you put a 3 there, 3 minus 2 is 1. The log of 1 to any base is 0. So instead of having the x-intercept over here, it's going to have it over here at 3, 0. And it's going to go like this. Something like that. Positive values of y, negative values. So the range for this one will be negative infinity to infinity. That's it for the video. Thanks for watching. We'll see you next time.